There's a sign up for the trip next weekend at the back. If you want to go, please sign up by the end of this. By the end of today. There's a second announcement was about the tours of Professor Clark's labs. It will be on Mondays, and there's a sign-up sheet for those as well. So if you're interested to see the lab, you should sign up, and there will be, I think, one tour next Monday and another tour a week from Monday, and I would like somebody to send a reminder about it to the Google group. So we actually have it in a written form as well. So I would suggest those announcements would be useful to circulate through Google Group, so we don't have them, see them here, and we'll have them on our mobile devices, so we don't forget. So I also, since we're getting close to the weekend, I expect you slowly recovering from this flooding of information from drinking from a fire hose or hydrant. So I would really expect those TA groups to organize discussions through the weekend. And there are plenty of mountaintops, you can choose one for each group. You can have a nice hike, and the best time to discuss things and when you're hiking up trails. This is really much more relaxing than sitting in a dark room. So I expect you to do that. And
if you hike down, it's also good.
By the time you hike down, you should solve the problem and starting a new problem by then.
Even at that time, you have to write the paper.
Absolutely. Any questions, organizational things? I know the T-shirt group is working very hard on the T-shirt design. So if you want to make an announcement on it?
Yes, just if you have any other idea, we have so far 3 or 4. So after the seminar, you can stop by and tell us your idea, because we are going to work on the draws this Sunday, probably, and then to have ready for this week.
Okay, so if you could send, or I mean maybe, so, but the work on Sunday will be just a group. Okay, fine. So everybody heard the announcement, or do you want me to repeat it?
So we have some questions about that. We thought that we are going to present the proposals and then we are going to vote.
Sure.
Or
the idea is to once you get some proposals, we're going to post them on the web, and we're going to have blind voting by the group, and whoever wins pays for the T-shirts. Yeah, it's all decided. So, any other announcements?
Just a quick one.
Yeah.
Please get in touch with me through the barbecue if you want to play soccer tonight.
Okay. So we have some fried balls there. Any other?
And get in touch with me if you want to play volleyball. So
okay.
There's a bit of a conflict.
There is a conflict. So can you schedule at different times?
It could be like one against the other.
Yeah.
One pushes your hand.
We need sand and grass.
Yeah, I think it's a good preparation for multiple, yes. Okay. Any other announcements about the organizational things? Yes. Yeah, and can you send that by email, by the... Okay, so we're done with social activities. This is unfortunately the makeup lecture. We went a little slow with the material I was planning to present, and I call it the dime lecture. I'm not going to explain why you have to ask Professor Grosberg about the reason why it's called the dime lecture. I want to start with reminding you so you've seen, I mean, we're switching back from the origins of life and the very previous derivations back to the sort of spiritual world of globology. And I want to introduce the main concept again, which is this intrinsic schizophrenia in polymer that it's trying at the same time satisfy two desires. It wants to be as many conformation as possible, so it wants to maximize its entropy. At the same time, if there's some kind of energetic contributions from either external or internal, it has to pay attention to that. So there's always a balance of those two evils, and they're sort of trying to compromise. And so depending on what those things are, we are getting different types of physics at end. And so just to give you a quick review of globology, I prepared the globology table here. And so if we are trying to stretch our polymer, we have this entropy fighting against this external force. And the blobs we're talking about are called tension blobs or Pinkus blobs. And from flexible polymers, we're switching again back to flexible polymers. The length scale of a blob is, with units, is the energy kT divided by the force you apply. So the way to think about it is, in any case, you have this very weakly, very small force. You're in linear regime always, and so the force is proportional to displacement, and the displacement, I mean the average distance. And I'm not talking about the whole chain. You can think about any subsection of the chain, because the force you're applying transmits throughout the whole polymer. So not only the whole chain, but any small part of the chain feel the same force. And so if you're thinking about any section of the chain of size psi, it could be the blob, it could be smaller, it could be bigger. It has G monomers in it. It has, if force is weak enough, force proportional to the average distance between the two ends. And there's no force, average distance between the two ends is 0. If there is a force, it's not 0. And the coefficient of proportionality is called the modulus, and the modulus is just kT divided by the mean square fluctuation size of that section. It could be the whole chain, it could be any subsection of the chain. So this is true in linear regime, and it's true, and so the blob is the boundary of this linear regime. If you go on a small scale smaller, this force, the work of this force on this section is less than kT. When you get to a scale where the work becomes of the order of kT, then this displacement, you solve displacement as a function of force, you get the displacement proportional to force divided by this coefficient. And when this displacement is equal to mean square fluctuation size of that section, then it begins to be important. It begins to deform noticeably. So when the displacement due to the force is equal to whatever the size of the section is, the energy that you put into the section is about kT, and that defines the size of the Pinkus blob, or tension blob. And so you have this blob size squared divided by kT times force equal to blob size. Solving this, you're recovering this simple relationship, that the force is kT over blob size, or the blob size kT over the force. This is true for ideal chains, for small chains, and this is the boundary of this regime. So if you have an ideal chain, then the force dependence on linear dependence of force and extension is true for all sections, not only smaller than the blob, but larger than the blob. In that sense, blob doesn't have any meaning. Everything is linear. If you are in a case of a good solvent, for example, then you are pulling, then this only works inside on scale smaller than the blob. On scale larger than the blob, you have to use whatever we did. And I'm not going to do it again. It's just basically a review. Any questions about tension blobs? Yes?
But it still has a meaning in the sense that it is the distance where the monomer of one chain starts to see monomers of other chains, right?
There is only one chain here.
I thought you were talking about the...
This is, I'm going to get to other, there's whole library of blobs, and I put this dictionaries to make sure you don't mix them up. It's like biology, you have to start classifying them.
I thought you were talking about,
No, I haven't got to those yet. This one is the tension block only. We are talking about single chain pulling by the ends, and we are not worrying about any other chains here. We discussed the confinement block or compression blocks when you squeeze the chain into either slit or a tube or a cavity, and then it is basically the size of the block is the size of the spacing to which you restrict your object. So it's very simple. The block is just the spacing, is the distance between plates, or the diameter of your cylinder and the tube, whatever you're thinking about, and flexible polymers, and then it's, in this case, the energy is going to be kT per the scale. Here it's also kT per block. In most cases, we're going to be talking about energies kT per those blocks, so that makes it much easier accounting. Any question about those two fields? Yes?
Sir, could you please explain again why is the energy of a confinement block, why is it equal to kT?
Okay, so on a very simple way to think about it is that you can draw your chain without any confinement. Let's do it. On a simple sort of scale. So you have your chain like this, and if it goes like that, basically and it continues on, whenever it hits the surface, you're making a reflection and making a decision for the chain to go the other way, and that costs you kT of entropy of making the decision. This is a very simple and probably wrong way of thinking about it, because when you get close to the surface, there are many possible collisions, and you have to be accounting for that. But the idea is that if you divide the chain into those sections, and for the chain without any confinement, it wants to go in space, it could be swollen, it could be ideal. When you take those sections and you place them, instead of going in a particular direction, you take this section and force it to be in there, you're making basically one decision for the angle between the center of mass of those sections. This is a very rough way of doing it. You can think about it in a more formal way, the way Professor Grosberg showed yesterday, in terms of ground state solution. You can solve the problem and look at clock and dominance and look at this first mode confined like a particle in a well, and that is that you're counting those modes. So it's basically you're confining a chain or a particle in an infinite potential route.
Yeah. So another simple way of thinking about it, almost what you said, is that you could think this is an entropy-only problem. So you could think of this as like confining an ideal gas, and every time the gas particles hit the wall, there's a pressure. So the same thing here. So the pressure, just the number of contacts times the polymer contact per unit area, and you just use this geometry to calculate the number of contacts.
Right. I mean,
And that gives you the pressure, and then you know from that how much work has to be done.
the only, I like this explanation. Is basically what I was thinking about. The only concern I have there is when you're thinking about contacts, this particular block can have, if you come close, and can have many contacts. So you're basically counting as one, even though there could have been other intersections. So within that caveat, it's sort of the simplest explanation to think about it. But this is confinement of a chain in a solution, isolated chain in a slit. If you have semi-dilute solution or a melt, confining that into a slit or a tube is very, very different. I will probably get to it at the very end of today's lecture, and probably as a challenge problem for the client.
So if the thermal blob size is smaller than the confinement, then you don't have this confinement blob, right?
Yes, you do, and I'll get to it. Well, yes, you do. We haven't got to the thermal blob yet. If thermal blob is less than confinement blob, what happens in a scale smaller than thermal blob, chain is ideal. On scales bigger than thermal blob, it's self-avoiding walk, but it still cannot cross the wall. So so the confinement blob wins on that scale and forces the chain to go back. If thermal blob is bigger than confinement blob, then chain is ideal on the scale up to confinement blob, and beyond it doesn't know. It is, and so you have to, it becomes a little bit different problem. You have to now worry about chain been falling back on itself, so you have to calculate. It now becomes a concentration block, which is something we'll get to at the end of, maybe in about 10 minutes. So it's a different problem when you're having chain overlapping back with itself. So if the chain, if the thermal block, so let me repeat it slowly. This is a good question, let's do it as a simple exercise. And so if you have the case of, I haven't covered the thermal blob yet, but you saw it 3 days ago. Thermal blob is less than confinement blob. Then the chain on very small scales, less than thermal blob, is ideal. So this is your thermal blob. And it forms a self-avoiding walkway of those thermal blobs. And then beyond that, you have confinement blobs that form and straight, in the case of cylinder, they stretch out. And so you have basically partially swollen chain of confinement blobs that stretches out. That's the easy case. In the case of thermal blob being bigger than confinement blob, then your chain is ideal all the way up to the spacing. Side confine. Oh, this is already just side confinement. It's ideal up to the scale, and so basically, if it was a very ideal chain, it would start forming a random walk and overlapping with itself over and over again. And so for a while it will be okay, except there is equivalent interactions. And so you have to know how to deal with the fact that it's going to be overpopulated. And the way to deal with this is to think about the section as almost, when the chain is reflected from the wall, it almost forgets its identity. So it's like many chain overlapping, like something we're going to talk about today, which is semi-dilute solutions. And so the blob that forces chain to stretch is going to be this multi-chain, something called correlation blob, and we haven't introduced it yet. So this problem you're not supposed to know how to solve yet. We'll do it probably in about 25 minutes. Other questions? I want you to ask questions because this is this session for questions mostly. I will produce new material, but I will make sure you understood the previous one well. Okay, so the third one we talked about is the thermal blob. And here you start with, again, you take your chain, you look at a subsection of the chain, you can cut it into monomers if you want. It's mostly dilute. And you can write free energy per unit volume. Free energy is volume of that section, psi cubed, times some virial expansion. You have second virial term, which I use V, but it could be V2 or A2. You have a third virial term. Why isn't there a first term here? Why isn't there a linear term? Why is there not? Why don't I have a main term, linear term, which is important to those solutions? But I want to calculate free energy of this section. Anybody? What does linear term mean?
It's for ideal gas.
Yes, it's for ideal gas. And so why isn't it there?
So this is the correction because of the interaction. So
No, this is the correction due to interaction. Where is the ideal gas term? Why don't I write ideal gas term? Can you speak up?
That's the reference rate that you're subtracting that from the ideal.
I'm not sure I understand what you mean by subtraction.
I mean, that is the reference rate. You're like, it's like shifting the origin or something.
No, because it's concentration dependent.
Don't really have energy dependence on single molecule.
Yeah, this is single molecule. This is I'm writing free energy for one section of the chain.
That's the interaction between.
This is interaction. Why don't I have? This is a virial expansion of interaction. Why isn't there a linear term?
Linear term means the interaction between monomer and
Linear term is not interaction. Linear term is what? Entropy. It's translational entropy of what?
Center of mass.
Huh?
The center of mass?
The translational entropy of center of mass of what? Of no. If I have linear term, it would have been linear. It would be entropy of gas of monomers, ideal gas of monomers. But my monomers are not free to move independently. They're part of one chain. There is only one piece of molecule. So center of mass of each monomer doesn't have. They don't have independent entropy. The entropy, the ideal non-interacting entropy of this section would be psi square over b square g. That's the right. We talked about it. The entropic part of section of a polymer, all of the entropy is conformational for the section. There is no translational separate entropy of monomers. That's why there is no linear term, because linear term would mean that those monomers can collide, freely move and collide with the walls of the container, and they cannot move independently. One monomer moves there, the next one has to move with it, they're connected. So that's why there is no linear term. There's only interaction terms, and if you want to talk about entropic part, it's this part. Is it clear? Ask questions, because this is sort of fundamental things.
This is the same thing that I was talking about yesterday. It was like F star, P star, mu star, all these interaction parts, not the ideal gas part. It is the same story as what we...
Yeah, we are repeating it now probably fourth time. You saw this first in the first lecture from Professor Pinkus in the very day. We are doing it over and over again, but we want you to sort of understand in what cases which terms are important and how to take into account. I mean, all of the physics is just basically balancing energy and entropy, and maybe sometimes do something a little bit more. So, if this really is very weakly interacting system, so the interaction is not very strong, less than KT, you can make all of those concentration is very dilute, interaction parameter is not very large. You can make this type of approximation, typically keep the first term that's important, and the concentration is just number of monomers, G, divided by the volume of this little section, and I can make the section so similar, larger, smaller, to decide what I want to study. I can plug in this into here and find out when this term, the first term, becomes important. What does important mean? Becomes of the order of KT. So when I plug this into here, I get basically, so the volume parameter times G squared divided by psi to the 6 because the square times volume psi cube. So I get this expression here. It's the volume parameter times G squared over psi cube. And it could be positive or negative, and I want it to be of the order of KT. That's why I put absolute value here. It could be minus KT or plus KT, depending whether it's attraction or repulsion. So this is the condition where I should not use this approximation on larger scales. I cannot use it on smaller scales because energy is small and it doesn't change conformation of the chain. So when otherwise on larger scales I have to balance this term against something else, and then you go into all this problem with Flory theory and other things that are wrong or whatever. On smaller scales there is no problem. The interaction is very weak, it's a perturbative. Perturbative interactions are always, you can always write this. So when this is small up, and so this gives you a boundary up to which you can sort of use this perturbation and be happy to wait with small linear corrections. So then you can, if this is really perturbative, chain on scale, smaller scales will be ideal. So it's going to have fractal dimensionality of 2, so number of monomers is equal to size of the section divided by the Kuhn length square, because fractal dimensionality is 2. You can plug this into this equation, and you get psi to the 4th divided by psi cubed times absolute value of v divided by b to the 4th equal to 1. You solve for psi, you get that it's proportional to it's b 4th Kuhn length 4th divided by absolute value of absolute volume parameter. This is the size of a thermal blob in both attraction and repulsion. It doesn't really matter because we're doing linear expansion on non-interacting chain. And it gives you a length scale at which this linear corrections become important, you have to do something else. And then you plug it back into here and find how many monomers there are, and it's going to be b to the 6 divided by v squared. We've gone through it last time, we're going to go to it.
So Michael, in all of this stuff, maybe it's good to emphasize, you're all being very cavalier about numerical coefficients.
Absolutely, we don't know anything about it.
But for this thermal blob, is there any argument to suggest that if you knew the numerical coefficient, that it's symmetric on both sides, or not?
I think so. Actually, when you define something like interaction parameter, which is basically number of blobs per chain, square root of that number, then if you go to formal theories, people do real calculations, not Mickey Mouse calculations, then they have, this is exactly the right expansion parameter for any calculation, but there is a prefactors here if you want to define, as a prefactor, like 1 over pi or 1 over 12, I don't remember exactly what this expression coefficient is. So, but I think it is symmetric. I don't
know, that's why I asked.
I think it is symmetric.
Do you know?
I don't know for sure, but I think it's symmetric. So, so basically, this parameter tells you whether the chain is really interacting in some serious way. Is it interactions are bigger than KT or smaller than KT? And if they're bigger than KT, how much bigger they are? If they're smaller than KT, then how much smaller they are? And that is just a fluid volume parameter divided by d cubed. Here I kept the sign because you can make z positive or negative. You don't need to solve this. This is slightly sloppy. It's a plus minus that depending whether you have attraction or repulsion. Times square root of n. So that interaction parameter is a formal expansion if you want to calculate chain size in different cases. Yes?
I have a question about those Mickey Mouse calculations. So suppose I have a real polymeric system and I derive the value of the size of thermal blob given this expression. So can I believe this value, or in other words, what is the size of free factor?
It's a order of unity. It's basically, I think this question, I mean, this question is, it's about the issue of the crossovers. If you want to calculate things using scaling in the limits, for example, let's look here. I'm talking about chain size, and I can calculate chain size, but this parameter is very, very small. I know the chain size is going to be Gaussian. I can calculate coefficient if I want. It's actually very hard to calculate coefficient, but this is the factor B, and there are some corrections from nearest neighbors hitting yourself back, and you have to really renormalize B. So this is not a trivial way of doing it, but people learn how to do it after a lot of pain. So you know what the span is. Then if I do scaling calculations, and I can calculate how this is supposed to grow for large positive Z, and then this is actually answer to Nikita's question. This is always going to be interaction parameter some power. That's why those exponents are always there correctly. No matter whether they're actual exact exponents or Flory exponents, the combination of exponents is the same because that's what comes interaction parameter. I can get that expression, and then I can try to extrapolate down and see where does do the two meet. And people have done it in simulations and experiments, and then you can get a prefactor in your thermal blob, and this has been done, and it's basically the biggest problem is people don't know how to carefully measure fluid volume parameter. So this is actually another way of measuring. So we have done, people have done careful experiment using second Weyl coefficients. You can measure it by scattering, and you can from that back calculate what the volume parameter is and find out this is approximately equal, what is the actual coefficient here. And it is of the order of unity. I don't remember exactly if it's 1.2 or 1.3, but it's very close to unity. It's not a large number. Other questions? Yes.
So Phil commented that it's symmetric, but I didn't quite get what is symmetric.
What is symmetric is that this expression here tells you the thermal blob is V force over V absolute value. So if I have V plus 100 cubic angstroms or minus 100 cubic angstroms, which corresponds to either strong swelling or strong collapse, then I think this definition, and in fact that's what makes this parameter continuous here, when you go from positive to negative, is that this relationship is symmetric and there is no large, typically when you go through transition there could be large amplitude ratio. You could have one scaling on one side, another scaling on another side, and there could be a big difference in coefficients. Here I think when you're close to theta point there is no big difference in coefficients, so it's on both sides roughly the same coefficient. Other questions? Okay, so this is just a summary of what we had before in terms of the solutions. You have a chain ideal when this interaction parameter is small compared to 1, meaning that you have less than thermal blob per chain, so number of monomers is less than thermal blob. It collapses or becomes a globular if you have, so the extrusion parameter is negative and smaller than -1, then it basically becomes a dense packing of thermal blobs. They attract each other with energy of kT, they pack densely. And we talked about that at the end of last lecture I gave. And so this expression, which is 1 thermal blob times number of thermal blobs to the power 1/3, is basically, if you do it as a swelling ratio, it's actually not swelling, it's a collapse. But it's a reciprocal swelling, it's size divided by ideal size. This interaction parameter to the power -1/3. You can just divide both sides by square root of n. And then if it swells, it becomes interaction parameter of this exponent, 2 nu -1. And that again, you can see exactly what we derive using Flory theory, using scaling approach. This is basically another way of writing it. Nothing new. It just gives you this ratio as a function of the universal parameter, which is convenient to collapse different experiments with different polymers and simulation on the same universal plot. Swelling on one axis versus interaction parameter on the other axis, and then the curve should all be the same. Okay, so that's end of the review of the first lecture. Second lecture, we talked about Flory-Huggins theory. I wrote it here in a way, this is Flory-Huggins free energy, which is not dependent on the choice of your cell or lattice. So it's a free energy per unit volume. It's volume fraction of A times log of volume fraction of A, which is component 1, divided by volume of A molecule, which is a well-defined physical quantity, plus y minus phi log y minus phi divided by the volume of B molecule. Plus here is the only part where you may think that what enters is the volume of the cell, but chi is defined per cell. And so actually chi also changes with the volume of the cell, so this whole combination is what really matters. And if you choose a different lattice spacing, you have to adjust your chi. So really what enters for free energy is this combination, times phi minus phi, which is probability of AB contact. So that is in the simplest form, where it's almost independent on choice of your lattice or spacing or something, but you have to be careful that if you choose pull chi from the table, they tell you for which V0 it was calculated. And what enters is the ratio. Okay, so then in the loose solutions, when phi is small, we did this expansion, and log terms obviously stayed, but all other terms became virial expansions, and we associated those coefficients. Second virial coefficient became 1 minus 2 chi times B cubed, where 1 came from entropy of solvent, and 2 chi came from interaction between solvent and the polymer. And that is related to second virial coefficient, and also I think it's related, we were talking about temperature dependence, to how far away you are from theta temperature. I think last time I divided by T, now I'm dividing by theta. This is linear expansion, doesn't really matter too much. It's next to the correction. So notice that large chi corresponds to negative second virial coefficient. So if I make a plot here of chi, exclude one parameter, and I'm defining 0 as the theta point, but exclude the volume equal to 0, no two-body interactions. And I want to compare it with the chi-axis. Chi-axis is going to go the other way. And what is going to correspond to 0? Anybody's awake? 1/2.
Yeah.
So chi-half corresponds to theta point. Exclude the volume parameter is 0, and that's our temperature. So I have a temperature axis here. This would be our theta point. So anything above, if this is positive, be in this expression that I haven't written, that relates chi to temperature. So I'm going to write it here. Chi was basically some constant plus b over t, and I'm talking about positive values of b. So high temperatures correspond to low chi. Heating, you go to lower chi. Lower chi means better solvent. So excluded volume parameter points always towards good solvent, chi always points towards bad solvent, and temperature can point one way or the other depending on the sign of this coefficient B here. Okay? Any questions? And then what we did, so chi going bigger than a half goes towards pure solvent, forming globules, and those globules like to stick to each other because their surface energy is attractive. They pay energy for extra surface, so if they coalesce, they're going to lower surface energy, and so they precipitate at some concentrations, and so there is going to be actually a phase boundary here. And there will be, as I'm going down, this is going to be my volume fraction phi, going between 0 here and 1 somewhere here, put 1 here. This is volume fraction phi, so this is pure solvent, and 1 corresponds to melt. And there's going to be a special region here, and I should have been doing slightly this scales. Something like that. And so we talked about taking derivatives of this equation to find the common tangent line, finding the spinodal and critical points, by taking corresponding derivatives of free energy, and the solution for the case of low volume fraction of phi is the critical point or critical concentration. For those who sit there may not see it, is 1 over square root of n, and critical chi is a half plus 1 over square root of n, and there is a second correction 1 over 2 n. We don't worry about it too much. It's there, but if n is large, this is much smaller. So on the scale of exclude volume or chi, this is of the order of 1 over square root of n. On the scale of temperature, the critical temperature is just theta temperature, slightly lower than this by 1 over square root of n. So this relative distance here between theta temperature and the critical point depends on molecular weight, and it's 1 over square root of n. So if n is 100, it's like 10%. If n is 10,000, it's only like 1%. So it's typically a few degrees, but if n is small, it could be tens of degrees. And I showed last time a phase diagram for different polymers, so you can look at actually see how this phase-to-phase region slides down as you go to low molecular weight, or it approaches this point, moving to the left and up as you get to high and high molecular weight, eventually going towards this point here. So this is two-phase, meaning what? If I prepare a system in this state, what will it do? A solution in this state, what will it do? Separates into what? So if I start here, it's going to separate into sediment or precipitate or something with concentration phi, I call it phi double prime, and a dilute solution with concentration of phi prime, of dilute solution of globules. We talked about globules extensively last lecture. And so this part of the diagram I mentioned is not quite correctly calculated in field theory, but it has sort of similar shape, it's just much sharper. The actual composition of the two phases depends on the lever rule. The closer you are to a particular branch, the more of that branch you have in your solution, and the less of the other branch, the ratio tells you by the ratio of those two sections. So this is a two-phase zone. Here, if you actually prepare it at very poor solvent, but to the left of this is called binodal, or phase boundary. If you prepare it here, this will get what? What would I observe if I prepare a solution at very low temperatures, but very, very, very dilute? What would I see in my solution? Would it precipitate? What would it do? It will be a homogeneous solution of what? Collapsed globules, right. So it's a dilute solution of globules. Okay, and we'll talk about this a little bit later, what happens on the other side.
But how do you know it doesn't sediment? That depends on the density.
What?
How do you know it doesn't sediment?
Because it's out, oh, because they're polymers, they have enough of KT.
Well, but the density.
Well, if you do, you're talking about if you centrifuge them in high G, they may sediment. Typically, I think they seem to be soluble. There's plenty of solvent inside. We're talking about cases where it's mostly water. It has a little bit of polymer, so the concentration of polymer depends on how big this parameter V is and how dense they are. But even colloidal particles of polystyrene typically not nicely soluble.
Well, because the density is close.
Yeah. So if
Depends
polymer,
what it is, yeah.
so if polymer, so there's a big difference in density between your globula and solvent. It may actually, you have to worry about gravity.
So this is phase diagram on the space station.
This is space diagram on the case of same densities, which is typically density of most stuff that I'm talking about is 1 gram per cubic centimeter plus minus 5%, typically, maybe 10%. Okay, so then the easy state is here. This is the case where if you are closer to theta line, what is the conformation of polymer?
That's it.
It's ideal, and we can calculate, so this is going to be stuff here. So here we have, again, dilute, ideal, and I'm going to put ideal in quotation chains. And so hopefully it's solution, because we don't worry about density too much. But they're swollen. I mean, they're ideal, so there's plenty of solvent in them. And then how far it goes in those. So and this line here. So how far? When does they stop being ideal? How much do I actually change temperatures, exclude the volume parameter, for my? So I stay in dilute solutions, and I want to know the boundary between ideal and globular state. What tells me the boundary between ideal and globular state? Anybody knows? Yeah, it's something that we already have done here. It's a blob size. So when my chain is becomes bigger or smaller than the blob, so this n over g, the same exact condition, z equals 1. So if my chain is bigger or smaller than the blob, it's going to be either ideal if it's smaller, or it's going to start collapsing if it's bigger. And this condition actually, on the scaling level, corresponds to the same condition as the critical point. Up to a prefactor, since we don't know the prefactor for scaling, we cannot say they're exactly the same, but all the dependencies on the interaction parameter is that this boundary, the critical temperature is about the temperature where the chains begin to form globule, collapse into globule. And this is actually, again, a symmetric zone. If I go on the other side, since this condition is similar on the other side, it will tell me how much higher temperature, how much can I increase my exclude volume parameter or decrease chi for chains to start to swell. It's again, when the thermal blob becomes smaller than the chain, or chain becomes bigger than the thermal blob, they begin to swell, and this gives me this condition, upper boundary of this. So this dilute ideal chain regime is all of this section here, and it's sort of like a symmetric on that side. On the scaling level, it's symmetric. Any question about that? So this is the easiest case. Chains are almost ideal. They far apart. They swim happily. It's a start increasing concentration. They start get closer and closer together. At some concentration, a volume fraction, they start seeing each other and overlap. So to find out this condition, what we can do is measure the concentration inside each chain and compare this concentration of volume fraction in the solution. So the volume fraction inside each chain is volume of one monomer times number of monomers divided by the volume of the chain, pervaded volume of the chain. So this is the physical volume divided by pervaded volume. So that's 1 over square root of n, and that's called overlap concentration. And for ideal chains, because I use ideal chain statistics here. And notice that this overlap concentration up to a prefactor that we don't know there, because who knows what is the volume of a coil is. I assume sphere, I didn't put 4/3 pi, total a sphere. So this is only scaling. And so this is maybe my definition, but this is approximate, and people argue, depending on who you ask, rheologists have one definition. This is when viscosity doubles of a solution compared to solvent. Scatterers have another definition. There are different definitions of overlap depending on different experimental groups. They like to define differently because there is no exact definition. You cannot really define it accurately. But for critical point, you can define it, and the critical point has the same exact dependence as this overlap definition. So basically, this critical point is roughly at the boundary between what we call dilute solution, and here we have semi-dilute solution. Okay. So this is semi-dilute CT solutions, and any questions so far? Then, if we keep increasing the interaction, chains begin to swell, and we know what their size is. We calculated it here, so we can figure out when these chains start to overlap. So here I have dilute swollen chain, dilute good solvent. So here we have dilute swollen chain. This regime here, and I need to know how far they're going to, this regime is going to continue. And the concern is the chains are bigger, so they're going to start to overlap earlier. So most likely, it's going to do something like this. It's going to go up, not the same shape as this, but it looks sort of like a similar region. This is a very different equation for this line and this line. This is a phase boundary. This is true transition. True thermodynamic transition. This is a crossover. Nothing in solution thermodynamically happens there, except physical properties are changing slowly from dilute to semi-dilute. So to do this calculation, I repeated the same one as here. I'm saying that for semi-dilute solution, phi star is going to be, again, the physical volume of the chain doesn't change if it swells, but the actual volume, I have to use the actual size, is going to be V1/5, B2/5, and 3/5 to the cube. I can calculate what that is and how it depends on n. I have n divided by n 9/5, so it's going to have dependence on n minus 4/5, and the v dependence is minus 3/5. So as my v is increasing, this overlap concentration becomes smaller as power 3/5 of this parameter is to the only parameter v. So this is the equation for this line here. So let me slides. If we continue on the board for the space. Any questions?
We want to emphasize that this dashed line at the lower end hits just exactly the corner of this.
Right. So this we haven't gotten that yet, but this line here, I'm going to continue on the other side. I haven't derived that part yet. In fact, this part of this line, which we haven't talked about at all, is pretty much symmetric reflection of this of the phase diagram. So there is a minimum of that. I mean, I haven't talked about this regime yet, but there is similar boundary between what we're going to call theta solvent regime and semi-dilute good solvent regime. To which I'm getting to right now. Okay, so this slide we went through last lecture. So we defined dilute solutions, overlap, and semi-dilute. And I said that the most important features of polymers is their ability to form semi-dilute solutions. So really the interesting part is the chains overlap. But they're far away and dilute. There isn't much change in properties. They're basically water or solvent, and chain have small corrections to physical properties of those things. So we've gone through all of this. So we talked about this dilute porous solvent for globals, and I've gone to this calculation and calculated the overlap concentration. So this is the equation for phi star. So it has this v to the minus 3/5 dependence, n to the minus 4/5 dependence. And so this is this regime here, where you have this now a more careful plot of this dashed line. So this is the boundary of the dilute regime. And as you go higher in concentration or higher fluid volume parameter, you're entering a new regime, which is what the main topic of the rest of the lecture. So, and the reason for the interesting part of that regime is a new blob appears. Something that you haven't had enough blobs, you have one more. This is actually the most important physical property of polymer solutions. And this is called correlation, blob correlation length. So if, for example, if you scatter from polymer solution, this is the length scale that's most apparent you can measure. It comes up in other measurements, like osmotic pressure measurements. I'll talk about it. So what is the physical meaning of this length? And what so I think this is a new generation, so I cannot use the CB analogy, but CB radio analogy. So if you had walkie-talkie, or you have those monomers like to talk to monomers on a different chain rather than monomers on the same chain because they're sort of tired of their own monomers. What is the range of the radio, of the walkie-talkie it has to have to be able to reach another monomer on a different chain? What is the, so definition is what is the average minimal distance between a monomer one chain and a monomer another chain? So this is basically a distance between nearest monomers on neighboring chains. So what is the importance of this length? So this is the picture of, so you have a solution, chains are overlapping, and you're dividing space into cells, and each cell you want to assign to a given chain. To do that, you have to choose a cell where most of the monomers belong to one chain. So all space is divided into cells, there is no empty cells, and each cell has mostly monomers from one chain. That is the idea of the correlation length. And so why is it important? Because if you are inside this scale smallest correlation length, most of the stuff around you are either solvent or monomers from your own chain. Because by definition, there is almost no monomers from other chains. And so we know how to deal with this. This is a dilute solution case. So here we can now say, okay, it's going to be either ideal or swollen, depending on how I interact with myself. So on scale smaller than this correlation length, it's basically dilute-like. Properties on this length scales are dilute-like. And then I can say that if there is solvent slightly, if I am above this theta line far enough, so my volume parameter is big enough, then my thermal blob will be small, and the chain will be swollen inside thermal blob, inside correlation blob. So this, my size of the section will be a swollen chain, like in the dilute solution, of G monomers. G here is number of monomers inside one of those cells. So this is the correlation blob. Again, it's a length scale where most of the monomers belong to my own chain, and just solvent and my own chain monomers around. So I can use these properties of dilute solutions and figure out what is the size of that section, depending on how I interact with monomers on my own chain. There's no screening because there's no other chains nearby on that length scale. And so it can be swollen, there's the volume parameter like that. And since I know how to calculate concentration on that scale, I can replace this n with g. I'm going to get some phi, not phi star for the whole chain, but phi star for those sections. So if I replace my n with number of monomers inside this blob, and then this gives me the fraction of monomers inside the blob, and this should be, since all blobs are the same, is going to be the selection of monomers in the solution. So since blobs are at overlap, they're basically filled space densely. Volume fraction inside the blob is the same as the volume fraction of the whole chain. I can plug this into G from here into there and find, you have two equations, two unknowns, and you can find how the correlation length changes with concentration. So this is a very important result. It tells me that the higher the concentration, the smaller are sections that belong to more than one chain. Eventually, at very high concentration, it's going to be just basically monomers. Because in a melt, there is volume correlation block is like one monomer. At overlap, correlation block is the whole chain. Any questions on this? I'm going a little bit fast, but I want to be sure. Yes?
Can you say anything about why the nearest monomer from a different chain would be the most prominent length scale in a scattering experiment? And not in the previous picture that seems so clear. In this picture, it doesn't seem as obvious.
In this picture, it's not as obvious. It will become obvious when we start talking about interaction between chains or statistically larger scales. Basically, at this length scale, if you're scattering with higher Q or smaller wavelengths, you're basically scattering from individual chains. And so your scattering structure describes the fractal structure of your chain. Your S of Q has fractal dependence. When you scatter on larger scales, you're basically now scattering from many chains at the same time, and many chains at the same time are behaving, the fluctuations of density that you have huge fluctuations in a single chain are getting suppressed. They're suppressed because chains, sections, larger scales interact with each other, and they don't want to overlap. On smaller scale, single chains don't care how, dilute solution chains don't care how they fluctuate because there's nothing to overlap with, there is no solvent. When you have other chains around, if you start fluctuating in density, which is what you're doing with scattering, you will have a penalty for interaction, which results in higher osmotic pressure in your C squared term, C cube cup, depending on what you're talking about, and they get suppressed. So we'll see in about 10 minutes that how to calculate osmotic pressure. It actually comes to be KT per that length scale. So what you see is a larger length scales, scattering becomes basically almost suppressed. It grows a square root of number of units. There is no more information about fractal structure of polymer you're scattering from polymer. So that basically you're crossing over from single chain fluctuating object to a solution, mean field average solution of just sort of weakly KT interacting fluctuating blobs. And there is no, this is in static scattering. Dynamic scattering is different. But the static scattering, this length scale comes out because at this scale you start seeing in scattering interaction between chains. So the distance between your monomer and neighboring monomer is a scale at which chains begin to interact. And that's what you pick up in scattering. Is that a reasonable answer for you? Phil wants to add something.
No, but what I'm worried about something else.
Okay. Okay. Yes?
I know you said that the dilute regime wasn't exactly symmetric, but can I still use...
The dilute regime is pretty, this part is pretty symmetric.
Yeah, so I can still use a critical chi as 1/2 minus 1 square.
Sorry. Critical chi comes from thermodynamics. This line we know exactly.
Yep.
And it's measurable very accurately. This line is defined up to with your technique. And so defining this point is always up to technique. If you want to choose it to be that point, be my guess, but there is no real physical reason to do it.
Okay.
It scales the same way, but coefficients we don't know. So it's convenient to draw it symmetric, but it's really, there's no physical reason for it to be symmetrically a reflection of a critical point, no.
But if you had a longer polymerization, you would expect that however you define it to move closer.
Well, everything scales finely, so as you go to high end, they both march in towards this point together. And in the scaling way is the same. I'm saying that the coefficients with which they march is going to be different. It could be a factor of 2 or pi. And it depends, since we don't know how to define these things exactly, there is, all of this is a phasing crossover regime.
Okay.
You can define it using techniques. You can, if we want to pinpoint, you can say, if osmotic pressure is equal to twice whatever, I call it this point. Then you have an exactly measurable line. But if somebody says, okay, I don't like to be twice, I want it to be pi, or golden mean, then you have another line. I don't think there's a physical exact way of pinpointing this because it's all depends on there is no physical phenomena occurring there, it's a crossover. Okay. So
This is all this without thermal blobs.
this is with thermal blobs. So okay, so all of this here, and this is what we're going to get next, is all of this region up here is occurring when thermal blobs are smaller than correlation blobs. So as you see, I'm using V here, and using V here meaning that I have done it using Z, and my Z was large for compared to, so my G correlation was bigger than G thermal, otherwise I would not be using this V here. So all of this is done when I'm placing my N with G. Actually, semi-dilute solution can be thought of solution of chains of that molecular weight. Having molecular weight much larger than that really doesn't matter for anything but dynamics and some other properties. From thermodynamic properties, it's really very, very small corrections. So you can think of it as those blobs. And the fact that it continues on doesn't matter too much for thermodynamics. So all of the properties depend only on this length, not of how long the chain is. Okay, so now what happens on larger scales? On larger scales, neighboring chains overlap with each other, then screen each other. And so you can think of this solution, you can start normalizing things, you can think of this solution as the melt of those volumes. You can replace each of those correlation blobs by new effective monomer, but mostly water, but has some polymer in it. You could make your chains as the chain of those correlation volumes. And then what you have is a melt of those blobs. And we have talked about, from point of view of Flory-Huggins theory, Flory theorem, and everything else, what is the statistics of the chain in the melt of blob, in the melt? It's ideal. So on these scales, chains are ideal. So you can find out what the size of the chain is the size of one of those blobs, correlation blobs, times number of those blobs to the power of one half. It's ideal statistics. And since we have the thermal blobs inside, there is some heat dependence. So the way to think about it, you have thermal blob, ideal, okay, I'll get to it in a second. So basically this is the picture. You have chains, so this is size of a section of the chain of little n monomers as a function of number n of monomers in a section, log, log, log. One Kunz segment has length b. As you keep on going, longer and longer chains, size of a section grows a square root because it's less than thermal blob, there is no swelling, up to thermal blob, so I'm inside those black circles. Then those black circles begin to repel each other, and I'm swelling, and the swelling continues until I get to correlation length. So this is G is the number of monomers in correlation blob, this is correlation length. So I have a scaling of 3/5. Then I'm getting another scale of a half, but for a very different reason. This half was because there was not enough exclude volume repulsion for chain solvent interaction to swell. This half is because of this magic cancellation and screening of heavily overlapping chains in a melt or in semi-dilute solution scales bigger than correlation length, which is the same as the melt. So we have 2 halves and 3/5 in between. So chains are partially swollen. Is that clear? So you have now several regimes and several different fractal dimensionalities. So I said all of that. Any questions? Okay. So let me see. I don't think I have time to do scaling theories. Basically, using deriving the same results using different method. You assuming that you calculate the overlap concentration. We did it here. You know chain size in dilute solutions, and then you're saying that in semi-dilute solution, the size of the chain is that in dilute solution some power of how far above overlap you are, this power x. You plug in size dilute solution, Flory size of the chain from here. You plug in phi star from there. So you get now expression for size as a function of the volume parameter. This one comes from, excuse me, 1 comes from size of the chain, 3x comes from the phi star to the minus x. So So you get this dependence to the volume, you have this dependence on number of monomers, this 3/5 comes from size, and 4/5 X comes from phi star, and you have also dependence for one fractions to X. So this is basically just formal assumption of self-similarity. Then what you're saying is that I know what should be the end dependence. On large scales, change should be ideal. Random walk, so this 3 press 4x over 5 has to be a half. I can solve for x, plug it back in, and I get my result that I had before. So this result that I had before can be obtained by doing the scaling and not putting in some physics at one point. This is where the physics come in, saying that this end dependence should be square root, because change should be ideal. Everything else is just self-similarity assumption. There is no physical, more physics the same as change is self-similar. The same exact calculation can be done for correlation lengths. I'm saying the correlation lengths and overlap is again the full chain, because the distance between chains is the whole chain. It again scales as some other power of y. All the algebra is the same. I just replace x with y. And there's only different one step. The same step here, when I said the chain size was ideal, I have to say the correlation length should not depend on n, because there's a distance between monomers, and it only depends on how chains overlap. It doesn't matter if the chain is 3 times more or 10 times larger. The distance, at the same concentration, distance between monomers will be the same. So this exponent has to be 0. And so I get a different solution for y. I get a different exponent. This is something else that we derive for correlation lengths. We derived in the previous slide. So you can derive the same results in 2 different ways. Yes?
Sorry, I have a question about screening.
Yes.
So in semi-dilute solution, you assume that the chain is a random walk of correlation blobs, right?
Yeah, you can derive it for thermodynamics.
Yeah, so, and this random walk is, it's ideal random walk.
Right.
So it scales as 1/2. So you allow your correlation blobs to overlap.
You're not allowing your correlation blob to overlap to the same way as you're not allowing your physical monomers in ML to overlap because of Pauli exclusion principle. Remember, in ML, chains are ideal, but you don't not saying that two monomers can occupy the same volume.
Yeah, that's true. But if you have a random walk and you do not allow your steps to overlap, what you get is not random walk, but self-avoiding random walk.
No, but I'm sorry. Let's just go back to theta point. So let me explain what second zero means. Having zero second coefficient can be done in 2 ways. Either have no interactions, or you avoid overlaps, but you give a price for being nearby just enough to cancel. So looking for far away, when I'm doing scattering, let's say I'm throwing one ball at another, and let's say the balls cannot hit each other, but they like to be nearby. So if you look from outside, it looks like they don't interact. So it's not really no overlap. So yes, I can have no overlap, but this is like a Mickey Mouse chains. Real chains cannot overlap, but they can interact, and the attraction well cancels hardcore repulsion. So the second virial coefficient is 0 because of the cancellation, not because they have no interaction. And so that's what occurs in this case. Yes.
So another question would be: is there any observable difference between ideal chain and that solid?
Well, yeah. Of course, I mean, we mentioned that, and I'm going to repeat again. This cancellation occurs only to the first order. If I start looking at actual fact that when chain comes back, it actually doesn't perfectly overlap, it's slightly shifted. There is a gradient term. The chain distribution is a Gaussian. If I add this Gaussian to the gradient, I'm getting a correction to the size. So, for example, R square is proportional to n plus square root of n. And the square root of n is a correction, but if I do a correlation function, bond correlation function, I'm going to see that my bond correlation function in ideal chain decays exponentially. In theta solvents or in MELs, the pace is power law, 3/2, it's now exponential. So there was a lot of work, and you can see the simulations, you can see the experiments, and there's a lot of papers, experimental, theoretical, not a lot, a dozen, recently, over the last 5-6 years that we're studying this deviation in statistics from ideality. There is also deviation of dynamics from similar. There are correlation holes, there are many features that are different, but on the roughest approximation, it's almost ideal. So the main term is ideal, but the corrections are there, and if your property depends only on the correction, if you cancel main term, then you see them drastically, like I was talking the correlation function, not decaying exponential is a big surprise. Ideal chains, if you walk past persistence lengths, you see exponential decay. Here, you never see exponential decay at all. You see only power law, which is very strange, due to loops. Yeah?
So it seems like from here that if you just continue to increase concentration, eventually everything will be ideal in all of the landscape. It sounds counterintuitive to me
Yes.
when I think about it.
Yes?
Is this right? If you,
Yeah. I'm going to get to this probably in about 10 minutes. This is correct. Okay, so I'm actually getting to it right now. So this correlation length decreases with concentration, as we derived here. As concentration becomes larger, correlation length becomes smaller, but thermal blob length doesn't change with concentration. And so at some concentration, the two become the same. And so this intermediate zone with partial swelling, the slope 3/5 disappears because correlation length moves towards smaller and smaller sections. Thermal blob, so let me get to this stuff here. So what I'm talking about is this regime here. This crossover depends on concentration. As you go to high concentration, it goes smaller and smaller and smaller, and this 3/5 zone shrinks to 0 at some magic concentration that we're going to call phi double star. So the way we calculate it is by balancing, equating correlation lengths, which we have expression here, in the thermal blob that I have expression down there, actually below this screen. So this is thermal blob is P force over V. This is correlation lengths, and then when I equate the two, I get a very simple expression for this phi double star, which is this line here. So this is line I call phi star. This line I call phi double star. Symmetrical with phi prime and phi double prime. In fact, phi double star has the same functional dependence on the excluded volume parameter as phi double prime in infield theory. So these two lines, up to coefficient P factor again, are symmetric, and there is a very similar, but there is actually a physical reason for this. If you remember, we talked about this concentration at the sediment. It was a concentration at which two-body attraction balances three-body repulsion. Very similar things occur at this length scale. Two-body repulsion is the same order of three-body repulsion. So it's not a transition, it's a crossover between regime where two-body repulsion dominating here and three-body repulsion dominating there. So here you have repulsion against repulsion, so it's not really anything to write home about. It's, in both cases you have things trying to expand. It's a positive osmotic pressure, but here it's dominated by three-body, here it's dominated by two-body. Here it was attraction and repulsion, that's why it was a phase transition. But the functional form is very simple. And so above that, so you can, this is when two or three-body thing balance, and chains above this is ideal on all scales. There is no longer this 3/5 law. So chain now is ideal on small scales because there's not enough interactions, or larger scale because of screening by surrounding chains. And there is never a swelling regime. And so all this, so let's see. So this is our diagram right now. You have this semi-dilute good solvent regime, and now I'm going to talk about this regime here, which is the ideal chain regime, but semi-dilute. Okay. Before I do that, I want to just to make sure we're on the same wavelengths. Let us take fixed temperature and change concentration and see what happens with chain size. Chains are swollen here. Here they begin to diswell. At this line they become ideal. So basically, if I plot size of the chain as a function of concentration above this, cutting through the semi-dilute good solvent regime, I start in dilute solution with a swollen chain using Flory theory. When I get to overlap, chains begins to partially diswell because on larger scale it becomes ideal. Screening by surrounding chain, it diswells following this 1/8 dependence for a while until it reaches ideal size and then it stops. And then above this phi double star, it stays ideal. As I keep increasing concentration to get to the melt, it stays ideal. Correlation length decays differently, it decays much steeper. Those solutions, it's not clear how to define. You can define the distance between chains, so maybe slope of one-third, minus one-third, I'm not going to talk about it. It goes as 3/4 for a while until phi double star, and then when it's here, we're going to talk about now. So any questions about this diagram? It's very important to understand the definition. Yes?
So basically, the curved line, the dashed line,
Yes.
which which physical quantity really changes from when you move from one side to the other?
Okay, for example, if we talk about osmotic pressure, if I am going to be on the left of this dashed line dilute solution, I can use 1/2 law, and all the higher order correction to 1/2 law would be basically in the, not important, and the osmotic pressure will be dependent on not only on concentration but also on molecular weight. It will be kT per chain. So it's going to be n-dependent if I go above this line, osmotic pressure becomes n-independent. It becomes only due to interaction between chains. If I keep on going further, going to this regime, it's actually going to change the dependence, so concentration will be different. Again, it's still n-independent, but now due to 3-body interaction, it becomes proportional to C cubed, not C to some other power. So there is a physical measurement, like osmotic pressure, which is a thermodynamic measurement, that is qualitatively different across here, but it's not a sharp transition, it's a crossover. It's a smooth transition from regime to regime. There is no phases. They're just different regions of physics. Not really different phases in the sense of, like this is really going to be a sharp, dramatic transition. You can see critical opalescence near this, there's a real phase transition. This is a smooth transition, but the crossover between different regimes, and the physics is different there. Rheology is going to be different. For example, here you have viscosity close to water. Here you have viscosity that grows very fast with concentration with very high power. Like fourth power of concentration, something very important. So things are changing physically, but smoothly. Any other questions? Okay, so in the case of a thermal solvent, then thermal blob is really monomer, and all of this occurs in the melt. So these regimes of 3/4 and 1/8 can continue all the way down to the melt. So phi double star in this case is basically melt. For the case of real thermal solvents. In real solvents, most solvents not a thermal, so you have this significant range of this what we call concentrated or semi-dilute regimes, where there is no partial swelling. Chains are ideal, but there's plenty of solvent, because interaction with solvent is not completely a thermal. So there's excluded one parameter is not extremely large. It can be 30% or 20%. Okay, so I talked about osmotic pressure a lot. In dilute solution, 1/2 law gives us ideal gas law, it's kT per chain. And then in semi-dilute solution, it becomes stronger function of concentration, and we can use the scaling, again, similar trick to determine what it is. So for phi below, phi star should be kT times f phi over n, it's ideal gas law, times some function, this function of phi over phi star, which is unity below overlap, and some power of this fraction, how much above overlap you are above overlap. So this is a third exponent z that I define. So I can again plug in dependence of phi star into this equation, and I find this dependence from phi star. Remember, phi star was n to the minus 4/5. It was 9/5 minus 1. So this 4/5 gives me times z 4 over 5. And there's extra 1 from 1/2 law, so I get this exponent of m. And there's another exponent of volume fraction, 1 plus z. 1 comes from 1/2 law, and z is from this extra due to interactions. So what do we know about osmotic pressure? Is due to repulsion between chains that are just adjacent to themselves. It doesn't matter how long the chain is, all that matters is where is the nearest monomer on another chain. So where's correlation length? So it should not depend on m. This should be 0 exponent. So from getting this exponent equal to 0, I'm getting this value of z equal to 5/4. And then plugging back in, I find the non-trivial exponent for osmotic pressure. Instead of square, as you expect from mean field, we see that it's actually stronger than 2, it's 2.25, 2.3. And it actually turns out to be basically kT per blob. So this is again back why those blobs are important, correlation blobs are important. At that length scale, neighboring sections of chains interact with energy kT, and the osmotic pressure is reflecting that. They repel each other with energy kT. Remember, in pore solvent, those blocks attracted with energy kT. That's why the polymer collapsed. Here, blobs repel the energy KT, and that gives you a positive osmotic pressure that's n-independent. Any questions about it?
And the fact that it's a higher exponent tells you that it's smaller than the mean field.
It's smaller than the chains actually more swell, they more dilute, and there is actually, and so the repulsion is smaller than mean field.
So it's phi is smaller than
Phi, okay. What you mean is phi is smaller than 1, so higher power, okay, in that sense. So, so this is the phenomenological form. You consider this basically 1. This osmotic coefficient, which is osmotic pressure divided by 1/2 or ideal gas, ideal solution term, is just this function, which is approximately, this is not a derived equation, this is a cheap way of doing crossover. It's 1 plus phi over phi star with extra power. Remember, it was 2.3 for the total exponent, divided by phi, that's going to get 1.3 here. So this is the data from different polymer molecular weights. You can see that osmotic coefficient versus concentration. At low concentrations, they level off, and you can get molar mass from these values. So this is low molecular weight, this is high molecular weight. But if you shift concentration to be by some overlap, again, overlap is defined after coefficient. Once you choose this coefficient and shift the data, you can find this nice overlap of all the data. And the slope here is pretty clearly steeper than 1. So it's clearly non-ideal, not second virial, not to body. It's the correlations of smaller chains are important.
What is the normalization in the y-axis that you choose?
It's called, what I'm plotting is called osmotic coefficient. I'm dividing osmotic pressure by the ideal osmotic pressure of a KT per molecule. It's called 1/2 law. So it's a ratio of osmotic pressure to the prediction if there was no interaction. And so that's why all the curves get to 1 at dilute solution, because at dilute solution, it is ideal. So that's how we're fixing it this way, and defining by C over C star, we force this line to go through 1 on this axis. And so by fixing this to 1 and that to 1, we get universal crossover. And the curve, this curve nicely fits through the data, and it's done for many, many different polymers. Biopolymers, synthetic polymers, they all fit the same way.
So it's worthwhile making a point here that this is the stuff that let the polymer scientists believe any of this stuff, because until then they assumed all this stuff was all crap.
You mean
physicist crap?
Okay, yeah, I think this is
This was the beginning.
This was the beginning, but I think also the scattering data.
Well, the scattering data was wrong. Was the error bars were bigger than the signal.
Okay.
So this was the only thing.
Where is it in the paper?
Nah, no, I wouldn't have any.
Okay.
The scattering papers, that was another sociology thing. That's a typical science you gotta be scared of. For the scattering data, which he didn't talk so much about, there was a prediction by De Gennes what the scattering should see in terms of these power laws. So the people did the experiments, I won't mention the name because I'm going to say something nasty about them, and they fitted it to, and they plotted it in a log plot, and it fits those power laws. But of course they didn't put in the error bars, and the error bars could have fit the mean field theory just as well. So the scattering theory, which was an experiment was supposed to prove this, proved nothing.
Well,
it was pure garbage. Because the error bars weren't good enough.
Yeah, but there is even more, I mean, on that, I mean, there's for a couple of decades, there was a big contradiction between experiment done in one side of Atlantic versus another in terms of dynamics. People saw mostly scaling exponents that agree with predictions of De Gennes and Europe, but here they saw something different, and it was a very, very long time when it was all reconciled. And I'm not going to talk about it. Okay. So now the final topic is the semi-dilute theta solutions. So what is happening here? Semi-dilute theta solutions, basically, what we have is chains are ideal, almost ideal everywhere. At any concentration, there is no concentration dependence on chain size. And so their correlation length you can still define the same way, what is the distance between monomers on neighboring chains. And you can use the same principle that they're dense packing of correlation blobs, so the volume fraction inside one blob is volume of a monomer divided by, it's basically similar to what I did here. The volume of a monomer divided by the size of a section to the power. So what you get is 1 over square root of g, which is b of xi. So the same exact, if you replace that n by g, this is the same calculation. So 1 over square root of n is the same as b of xi, because ideal statistics, fractal dimensionality is 2, exponent here is 1/2, dependence xi. So you can, so this tells you that volume fraction and correlation are reciprocally related. So there's no anomalous exponents here. Its xi is 1 over 5, and so you can you could use scaling to derive the same way. I'm not going to do that, but it's the same exact calculation. I'm going to skip this derivation, but you can derive the same result. So the question is, what is the meaning of it? Because there are the same statistics of the chain on smaller scales and on larger scale. There is no change on the correlation lengths in good solvent. Chains were going from swollen to ideal because you had screening of excluded volume interactions. Here it goes from ideal to ideal. So what is the what's such a big deal about correlation lengths? What is the difference between theta solutions and ideal solutions of ideal chains? Yeah?
So that's what I thought you said in the first start of the lecture. The correlation still means when does a monomer of one polymer begin to see monomers of other polymers in the same?
Yes.
So that's the meaning of, is there more than that?
Right, so if I had two boxes next to each other, one is the box is semi-dilute solvent of ideal chains, another the box is the same exact concentration, same exact molecular weight, non-interacting chains. The statistic will be the same of each of polymer. What would be the difference?
What do you mean the difference?
If I look at it, I have two boxes.
Yes.
What would be the what would be the biggest difference between two solutions? Ideal, I just throw completely ideal chains on interacting in one box. Here I'm throwing ideal chains, but they're theta solvent, so their second virial is 0, or they are screened by other chains, but they are still semi-dilute theta solutions. So what's the difference between semi-dilute theta solutions and the same exact, if I turn all the interactions and chains stay the same size, what would be the difference between two boxes?
Is there a difference with
No.
I guess the question, that's the quizzes. Yeah, I'm not, I want you to think.
A coefficient maybe.
Coefficient in what? In the size? Oh, no, I'm making them the same size. Coefficient is 1. It's my chain, I can do anything I like. Anything else? Yes?
I think the answer to this question, I think the answer to this question is the same answer for my question about the difference between theta solution, globulin, theta solvent, and ideal random walk. So below correlation length, it will be an ideal random walk, and above correlation length, it will be.
It's not ideal below either. We talked about it. In theta solvent, there are still the same loops, and actually there is actually two independent groups, but they show there is this correlation length of 3/2 is observed both in melts and in dilute theta solutions, and it has very similar physics. Coefficients slightly different, but the physics is the same. So no, they're almost ideal in both cases. Yes.
Is it that in the theta one we have a preferred length scale we can identify, or?
Which is distance between chains, average, right, between monomers. I can define in the other box as well. I mean, I can go in that box, I can measure distances, I can define lengths, and it's going to be the same length.
No, a specific length scale which depends on the overall concentration.
Right, but I can do it in the other solution. Like I can have non-interacting chains at low concentration there will be no overlapping, and as I increase, I can throw more and more overlapping chains that start overlapping. I can define the same parameters. So is concentration the same, statistics the same, I'm just throwing them in. What is the difference if I look at them, would they look the same? Or would they be noticeable difference?
The correlations look different.
Huh?
The correlation. Scattering looks different.
Scattering would be different. Why would it be different?
At length scale smaller than the correlation blob, you see whatever walk the...
But the ideal in both cases, so there should be the same.
But then at longer scales, then the correlation length then it dies off because it's screened by the...
Thank you. Okay, that's the correct. So the point is that yes, they're ideal, but there is distractions. Second virial is 0, but the third virial is not 0. And the third virial, I didn't tell you, I didn't turn off the third virial coefficient. the third virial coefficient makes those chains repel each other, and so the fluctuations of density will be suppressed by the third virial coefficient, and so the solution, similar solution, would look very uniform on larger length scales with correlation lengths, while the random chains would look completely huge fluctuations of density on very, it's ideal gas of chains. So there will be much bigger fluctuations. So scattering, osmotic pressure, just looking at them in a microscope, you have